You will remember that we are looking at forces, Newton's laws and such, and we've sort of covered, we spent a great deal of time on Friday, I guess, talking about Newton's first law and getting into Newton's second law a little bit as well. So I want to talk a little bit about that. Then we're going to get doing some drawing right away, some free body diagrams, and we'll soon be moving into the word problem segment of the unit. Nicholas.
Was there a handout for project?
No, I think it was all done in the clickers, if I'm not mistaken. Am I right?
Yeah.
Okay. Okay, so you've got a handout here. This one really has only one single question. It's more sort of a reading. But you can make little notes or highlights or whatever you want on that handout. So, Newton's second law of motion, the big misconception. So what's the big deal? Many people have known Newton's first law since 8th grade or earlier, and if prompted with the first few words, most people could probably recite the law word for word. And what is so terribly difficult about remembering that F equals ma, right? You've probably used it in grade 9. We're going to use it some more in the near future. It seems to be a simple algebraic statement for solving story problems. The big deal, however, is not the ability to recite the first law, nor to use the second law to solve problems, but rather the ability to understand their meaning and to believe, actually believe their implications. While most people know what Newton's laws say, many people do not know what they mean, or simply do not believe what they mean. They may say they believe it, but when they are asked a situation that would require the use of one, they don't actually apply it. There might be a better way to describe that. So cognitive scientists who study how people learn, have shown that the physics students come into physics class with a set of beliefs which they are unwilling or not easily willing to discard despite evidence to the contrary. These beliefs about motion, known as misconceptions, hinder further learning. So the task of overcoming misconception involves becoming aware of them, considering alternative conceptions or explanations, and making a personal evaluation of the two competing ideas, and adopting a new conception that is more reasonable than the previously held misconception. Leroy, you need one of these. This process involves self-reflection to ponder your own belief systems, critical thinking to analyze the reasonableness of two competing ideas. What's that law called where you have to pick the simplest one?
Parsimony.
Law of parsimony, right? Now, oddly enough, the simpler explanation is often so simple for people that they think that it's weird or that it's difficult or that it's challenging, okay? And it's not often until much later, sort of, as you sort of do some more studying and some understanding, that you really understand that it's simple, okay? Most people find simple challenging, oddly enough. Self-reflection, critical thinking, and evaluation. While this process may seem terribly complicated, it's simply a matter of using your noodle or your brain. Okay. So the most common misconception is one which dates back for ages. It is the idea that sustaining motion requires a continued force. If I want to keep something moving, I have to keep on pushing, right? I had to push my golf cart the other day to keep it going because I blew the engine. If I have to keep it going, I have to keep pushing. I can't just give it a shove and let it roll on itself. How come? Friction. Friction is that, it's just always there, causing grief. Okay? The misconception has already been discussed in the previous lesson, the one we did on Friday, but will now be discussed in more detail. This misconception sticks out its ugly head in a number of different ways and in a number of different times. As you read through the following discussion, give careful attention to your own belief system. View physics as a system of thinking about the world rather than information that can be dumped into your brain without evaluating its consistency with your own belief systems. And I would even add on to that, physics is a lot more about thinking and a whole lot less about memorizing. Okay? How many people generally, and you don't have to put your hand up or not, but just sort of think about it on your own, right? When you think about science that you've had up from kindergarten right to grade probably 8 or 9, right? A lot of science has just been memorize some facts, right? Write a test, give the facts back to the teacher, right?
Oh, that's bio.
And there's a lot of bio, that's right. Certainly people would agree with that, right? And are some people struggling in here because I don't do that? And again, you don't have to answer, but think about that. And the answer is likely yes, okay? Memorization will not get you very far in physics. You got to think. Newton's laws declare loudly that a net force, an unbalanced force, causes an acceleration. Let's highlight that. A net force causes an acceleration. An acceleration is simply a change in motion. I sure wish I knew what happened to my highlighter pen. I don't like any of those. A net force causes an acceleration. Net force causes an acceleration. The acceleration is in the same direction as the net force, and that comes into play quite a bit when we start dealing with circular motion in grade 12. To test your own belief system, consider the following question, and its answer is C by clicking the button. Now, we're not actually going to click any button here, and obviously you have a piece of paper that you can't click on. Okay, so here I have a picture, one that looks similar to one you've seen before. Two students are discussing their physics homework prior to class. They are discussing an object which is being acted upon by two individual forces, both in a vertical direction. The free body diagram for that particular object is shown at the right. So this is called a free body diagram, and we're going to be talking more about those later in the day. Okay, you're going to be drawing some. During the discussion, analytical, pausing for Sean to laugh, suggests to the two students, first girl, her name is analytical. Okay, I'll try the next one. She's talking to her friend. His name is Noah Formula. Yeah? It's not funny? Analytical and Noah Formula. The analytical suggests to Noah Formula that the object under discussion could be moving. Anna says this object right here could be moving. In fact, Anna suggests that if friction and air resistance could be ignored because of their negligible size. What does the word negligible mean? Anybody know? Negligible?
Not eligible.
Yeah, it's pretty close, really. Yeah. No? Nobody? Negligible just means that it's so small that it really doesn't matter. So small that you don't have to worry about it. Okay? The object could be moving in a horizontal direction. According to Anna, an object experiencing forces, listen carefully here. According to Anna, an object experiencing forces as described at the right could be experiencing a horizontal motion as described below. She's saying this object here could be moving. Could be. Noah Formula objects, arguing that the object could not have any horizontal motion if there are only vertical forces acting on it. Noah claims that the object must be at rest, perhaps on a table or floor. After all, says Noah, an object experiencing a balance of forces will be at rest. Who do you agree with? Do you agree with Anna that says this could be moving? Or do you agree with Noah that says, no, it has to be at rest because the forces are balanced? I want you to write down your answer. And rat out your neighbor if they don't write something down. All right. So here's what I want you to do. I want you to look at your neighbor, and I want you to answer for them. Okay, I want you to answer for them. How many people agree with Anna, who says it could be moving? Anna says could be moving. Noah says it must be at rest. How many people's neighbor says Anna? How many people's neighbor says Noah? No. Your neighbor says Noah? Brian, your neighbor says Noah. Is that right? Okay. Well, it's pretty obvious who's more popular here, and the answer is yes. Could be moving. Could be moving. Because if it's already moving, an object in motion stays in motion. An object in motion stays in motion. Could it be at rest? Oh, yes, it could be, Connor. Do you guys need to wrestle or something or other? Or? It could be moving, so the correct answer is it could be moving, but it could also be at rest. Could be moving or could be at rest. Okay? That's the correct answer. Let me get Noah out of the way here. Could be moving or at rest. Okay? Certainly an object that's just sitting on a table would experience forces similar to this. Okay? Remember last park when you went sledding down the hill and across level surface at the local park? And I got this off the internet somewhere. Apologies extended to those who live in warmer climates who don't know what tobogganing is. Of course, we all know about that. imagine at the moment that there was no friction along the level surface from point B to point C, and that there was no air resistance to impede your motion. How far would your sled travel? And what would that motion be like? How far would the sled travel if there was no friction and no air resistance?
Forever.
Forever. And at a?
Constant speed.
In a straight line, right? Straight direction. Exactly. Okay? The sled would travel forever at a constant speed. Without friction or air resistance to slow it down, the sled would continue in motion with the same speed in the same direction. The forces acting upon the sled from point B to point C would be the normal force, which we're going to talk about shortly. The snow pushing up on the sled, and the gravity force, and there's the diagram. These forces are balanced, and since the sled is already in motion at point B, it will continue in motion with the same speed and direction. So, as in the case of the sled, and as in the case of the object, which Noah and Anna are discussing, an object can be moving to the right, even if the only forces acting upon the object are vertical. Forces do not cause motion, forces cause accelerations. And if there's anything you want to highlight, it's that last sentence right there. Forces do not cause motion, forces cause accelerations. Okay? And what are accelerations? Changes in motion. And maybe we should write that in. Okay? Forces do not cause motion, forces cause changes in motion. Okay? And you might have to think about that a little bit to sort of truly get the difference. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across the table and watch it slide to a rest position. The book in motion on the tabletop does not come to a rest position because of the absence of a force. Rather, it is the presence of a force. That force being friction, which brings the book to a rest position. In the absence of a force of friction, the book would continue in motion with the same speed and direction, forever, or at least to the end of the tabletop. A force is not required to keep a moving book in motion, and a force is not required to keep a moving sled in motion. And a force is not required to keep any object, horizontally moving object in motion. Okay? Forces are not required to keep objects moving. That is all. So we're going to, did I not get to?
No.
Alex, I apologize. Not a problem. Okay, so we're going to be looking at drawing some free body diagrams, okay? So I'm going to give you about 4 or so examples, and then you guys are going to get a chance to do some. So, free body diagrams, otherwise known as FBDs, are simplified representations in a problem of an object called the body and the force vectors acting on it. This body is free because the diagram will show it without its surroundings. In other words, the body is free of its environment. So they are extremely simple diagrams. You don't need all the extra stuff around it. Okay? This eliminates unnecessary information which might be given in a problem. Let's take this figure to be a pictorial representation of a situation, a sled on snow with a horse pulling it. First, we'll represent the sled, the body in our problem, as a really simplified figure, a square resting on a flat surface. They generally draw these as squares. Some books prefer just to use a dot as sort of like a center of mass and go from there. In this tutorial, we'll review some of the main forces that you will encounter in physics and discuss their contributions to an FBD. So they are gravity, normal force, friction, and a push or pull. So number 1 is important, obviously, gravity. First force we're going to investigate is that due to gravity, and we'll call it the gravitational force. I call it the weight force. Same thing. We know that the acceleration due to gravity upon Earth is approximately 9.8 meters per second squared. If you didn't know that, you need to know that. 9.8 meters per second squared. The force by Newton's second law is Fg equals mg. Now, where does that come from? Well, it comes from Newton's law that says F equals ma. The acceleration is due to gravity. Okay, so we usually substitute the g with an a, Connor. And I tend to write Fw because I call it the weight force. Okay, so I tend to write Fw equals mg. So let's add this to our diagram, and you should have it over here on the right already. Do you have it there? Over on the right? Okay. Note that the force vector labeled Fg or Fw points downward, as this is the direction in which gravitational force acts. And we should write in here that downward is negative. Right? Down is negative. Note that also that this force is commonly called the weight. The weight, mg, is different from our everyday use of the word weight, which is known in physics as mass. When someone asks you how much do you weigh, You really want to know what your mass is, right? Weight is actually measured in newtons. How many people out there have a bathroom scale that measures you in newtons? Anyone? My weight force is 751 newtons. F equals, FW, yeah, let's rewrite that a little nicer. FW is equal to mg. What's my weight force? 751 newtons. Mass times gravity, 9.8. What's my mass? 751 divided by 9.8. Somebody please, with a calculator. 751 divided by 9.8. 76.5. Really? 76.5? Kilograms.
That's how I see it.
Kilograms, exactly. 76.5 kilograms. If you want it in pounds, you're going to have to multiply by
9.4.
2.2.
That's divided.
2.2. Yeah. Okay. So yes, if someone asks you how much you weigh, go right ahead and say, like, you know, anywhere from 500 to 800 or 900 newtons. Okay. I'm sure they'll be thrilled with that answer. Okay, let's talk about normal force. The normal force is one that prevents objects from falling into whatever it is they're sitting upon. It is always perpendicular to the surface with which an object is in contact. Highlight that, Sonia. The normal force is always perpendicular to the surface. Always. Connor. Always what, Connor?
Negative?
You weren't even listening, were you?
Nope.
Always perpendicular. For example, if there's a crate on the floor, then we say that the crate experiences a normal force exerted by the floor. Because of this force, the crate does not fall into the floor. The normal force on the crate points upward perpendicular to the floor. It's called the normal force because normal and perpendicular mean the same thing. Oh, don't do that. The normal force is always perpendicular to the surface with which a body is in contact. For example, a body on a sloping surface like a ramp, the normal force acting on the body is still perpendicular to the slope. So in this case here, that's my Fn. Okay, it's always perpendicular to the surface. Now gravity is always straight down. Okay, so two different things. Most of the time, the normal force is exactly opposite to gravity, like this. But when it's on a ramp, then it's perpendicular to the surface. Okay, that's important when you get to grade 12. Okay, so let's add a normal force to our FBD and represent the normal force with the letter Fn. Fn can also be written as F and then a, you guys know what that symbol means?
Nope.
Perpendicular. Have you seen that before? Geometry maybe?
Mm-hmm.
Okay. Fn for normal or F perpendicular. Friction is the next one. Related to the normal force is the frictional force. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular to the surface, the frictional force is always parallel to the surface. Furthermore, friction opposes motion, so its vector always points away from the direction of movement. Away from the direction of movement, or intended movement. Friction is divided into two types, static and kinetic. These are represented by FF, which with a further subscript, S for static friction and a K for kinetic. Static means at rest, kinetic means moving. It is the force that makes it difficult to start something moving. On the other hand, kinetic friction occurs when the body is sliding over the surface. Of course, rolling objects experience friction as well. Rolling friction is actually quite complicated, so we're going to assume everything is sliding. This is the force that causes objects to slow down and eventually stop. Friction is usually approximated as being proportional to the normal force. The proportionality constant, is called the coefficient of friction. The coefficient of friction. Now, you may remember the day when you wandered in and there was some pancakes grills in the room, right? And we determined, we'll get there. We determined the frictional coefficient between pancakes and Teflon grills. Okay, there's a number. Mr. Schmidt's brother is a biochemistry or biomechanical engineering professor. He measured the frictional coefficient between an eyeball and an eyelid, how much friction there is, and how to reduce it. Okay? So frictional coefficient is a number, how much friction there is.
What we get out of that
He actually, so the letter that we use for coefficient of friction is the Greek letter M, which is called mu, and it looks like a funny looking U. It's got a big tail on the front of it. Okay, it's the Greek letter mu. It's Greek letter M. The coefficient is represented as mu s for static friction and mu k for kinetic friction. The numerical value of mu depends upon the nature of the surface in which the body is in contact. Just so happens that we determine that the friction force, frictional coefficient for pancakes is 0.49. Just a number, 0.49. Okay? Slipperier things like curling rocks on the ice would have a much lower coefficient of friction. Turns out when we let the pancake cool, the frictional coefficient went down quite a bit. Another force that may act on an object could be any physical push or pull. This could be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, the horse pulling on the carriage. We will label the applied force push or pull with an FA. Now, I didn't mention this, but our friction force is to the left here. Generally, when we draw pictures, we assume they're moving to the right. We sort of live in a left to right world. Can you tell that this object is moving? Like, what would analytical and NOAA formula say? Is this object moving?
Yep.
How can you tell that? You're just guessing? You guessed right. How can I tell that this object is moving? Because there is a frictional force. There's a frictional force, so it has to be moving. Now, hold on here. I said before, when I push my filing cabinet, you were going to say that? But how can I, what's the difference? How can I tell that one has to be moving, even though I can push on the filing cabinet, friction will push back on me, filing cabinet doesn't move? How can I tell this one it has to be moving? Because there's no applied force. There's no push or pull, right? So it has to be moving, and in fact, friction is slowing that one down. So if you have an applied force, okay, usually we write that as FA. We will label the applied push or pull force with an FA, okay? Now, generally, as a rule, whether it's a push or not, we always draw things away, okay? So even if I'm pushing it to the right, I still draw the force coming from, showing more like a pull. Okay, even if it's pushing, we tend to draw them like that. Tension in an object results if the pulling force acts on its end, such as in a rope used to pull a boulder. If we say that our carriage is being pulled by a bar by the horse at the front end, then we can add this force to our FBD. There we have it. All the forces acting on the carriage have been labeled in the figure. This is a complete FBD for our problem of a carriage being pulled along a rope. You have to label them. You're going to be asked to draw FBDs. You have to label them. And they have to be proportional. What do I mean by proportional? What do you think? Like, if the applied force is bigger than the friction force, numerically, then the arrow has to be bigger than this one. Okay? Like, if it's twice as big, you get, say, 10 newtons and 5 newtons, the 10 newton one's going to have to be twice as long, twice as big. Okay, let's talk about a couple examples. Here's example number one. The child next door wants to take his German Shepherd named Spot for a ride on a sled. He chases Spot, who's running away, while dragging his sled behind him. What forces are acting on the sled? Okay, so you're going to draw. You guys have a blank one there? Have you flipped the page over? The one with the sled? Okay, so let's consider each of the above forces in turn. Since the question does not state otherwise, we will assume that it's happening on Earth. Pretty good assumption. Okay, so gravity is drawn. So go ahead and draw FW in there, the weight force. And it's down. Okay? I can't think of a free body diagram that's not going to have gravity on it. The sled is being dragged in the ground, which we can be taken to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. Thus, there is a normal force N on the sled. And so that is going to be up. Now, do you need to get your ruler out and measure them to find out if they're exactly equal? No. As long as they're within, if I eyeball it and they look about the same, then we're good. Right? But if one has to be bigger than the other, make sure it's bigger than the other without getting your ruler out. Because the sled is in motion, the surface with which it has contact, the ground, is not frictionless. It didn't say anything about that. Then there is kinetic friction. And as I said before, we tend to make things going to the right. So my friction force is going to be backwards to the left. And the kid is pulling on the sled, so there's a pull force F pull. The pull may not be parallel to the ground, but at an angle is shown. So there may be, if this kid is taller, the applied force might be at an angle, like so. That's an FA. that all good? Okay, Dot and Spot. Spot, the German Shepherd, is being walked by his best pal Dot, the Siamese cat. Oh, I've already got a drawing here. Actually, Dot is pulling Spot across the ice rink and disturbing the neighborhood hockey game. What are the forces acting on Spot? Well, once again, it's on Earth. And so I've got a weight force down. We're going to assume that ice is frictionless. When they talk about ice surface, that's physics code for no friction. Loosely packed snow is physics code for some friction, but not a lot. Okay, rough ground would be physics code for lots of friction. So no friction. Now, what do you think this red one over here is? It's me talking about that stuff that I was talking about before. So that one is, if it's a push, we don't draw pushers, we always draw pulls. Okay? Oh, because there's weight force, there also has to be a normal force. And because he's on a leash, we're going to label this as a tension. I don't get too excited about that. I just label everything applied force, FA. Okay? Any questions about any of that stuff? Good? Too fast? Too slow? Just right? Okay, King Kong's pendulum. While climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging around outside of skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? I didn't make this up, Lloyd. Gravity. Is there a normal force? He's not on a surface, that's why. He's hanging from a vine. So is there a surface pushing him up? No, there is not. Okay? Is there any friction? He's not on a surface. The only friction that you could argue would be some air resistance, which I would gladly accept. Okay? If you want, you could have a little bit of air resistance there. But generally, the only thing holding him up is the vine or the tension. Right? And I just assume write it applied force. What could you say about the value of the tension? What would it be equal to? Like if it wasn't King Kong, if it was me swinging on a vine and my weight is 751 newtons, how much tension would be in the vine? 751 newtons. Approximately. All right. Instead, now, King Kong has had enough of monkeying around. Thank you. And has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building, only this time he's gotten lazy and he's taking the elevator instead. While he is riding up to the top of the building at a constant speed, what forces are acting on him? At a constant speed. Is that important, that it's a constant speed? Why is it important? What does it mean? If there's a constant speed, then what does that mean? I'll give you a hint. What does that mean about the net force? Equal to, I heard someone say it, 0. Which means all the forces must be balanced. All the forces must be balanced. Okay, so we know that the elevator is going to be subject to gravity, so I've got a weight force. Is there any friction involved here? He's moving, constant speed. There's likely some friction between the elevator and the rails and all that. But really, we're just talking about the forces on him, King Kong. So really, all there is a normal force up. There's only a normal force up. And it's at a constant speed, so these two things have to be equal to each other. Do elevators tend to travel at constant speed? They sort of have to, right? If they accelerate all the way to the top, you'd be going pretty fast when you got to the top. Right? Having said all that, when you get on the elevator, it's obviously at rest, and it has to do what? Speed up, right? It has to speed up. So at the start, does there have to be more than the normal force, more than your weight force? Like if I stand in an elevator with my 751 newtons, does it need more than 751 newtons to get me going? Like maybe 800, right? And then once they've got me going, then what do they need? 751. Any more, and I'll be accelerating all the way to the top, which wouldn't be good. Okay? So these two have to be balanced. that the last one? Okay. Wow, we've moved through things quite quickly today. This is awesome. Okay. So you're going to have a chance here. There are 11 to try.